Here is a green liquid, but green isn't always what it seems. So what's going on in this experiment? How can you replicate it? And what's the science that's going on? In this video, we'll have a look at that. We'll think about some international considerations about choosing the correct dyes, and we'll also think about how we can do this using dyes that dissolve from glitter. And for those of you who hate this stuff, we'll also look at a version that does not. Pick yourself a vessel that's going to be the right kind of size for your audience. Medium-sized test tubes, boiling tubes, they work quite well. I like these sample vials because they've got a flat base and a screw-top lid. For larger audiences, a graduated cylinder with a stopper on top, that might work well for you as well. If you don't already have volume measurements, you will need to know the maximum capacity of whatever flask it is that you're using. This one here actually has a maximum capacity of 40 ml. I need at least a quarter of the volume overhead to be empty for adding some powder later. Obviously, you can leave more space. I'm also making my life easier by choosing a value that I can easily divide by 3. You'll see why in a bit. The two liquids I'm using for the first version will be water and acetone. In goes 15 ml of water and then 15 ml of acetone layered on top. It doesn't come out very well on camera, but holding up to the light, closer students might be able to see that the lower density acetone sits on top. Now, when I shake, keep an eye on the temperature. You might want to hand around the flask at this point because it actually gets surprisingly warm as the water forms strong hydrogen bonds to the acetone. The liquids have mixed. What's going on? Well, here's a crude model of some water that I've made. Please forgive me, the big spaces between the molecules. In reality, of course, they're all in contact with one another. But when our water molecules are lining up in the right way, with lone pairs of electrons on one molecule pointing towards the hydrogen atom of another molecule, a strong intermolecular force known as a hydrogen bond can occur. We need two things for this. Firstly, a highly electronegative atom like nitrogen, oxygen, or fluorine, which has a lone pair. And secondly, that atom must be directly bonded to a hydrogen so that it strongly pulls away the bonding pair of electrons from the hydrogen towards itself. Water satisfies both of these requirements. I'm showing lone pairs with these little hybrid bubbles and that strong intermolecular force, the hydrogen bond, with these green arrows to represent an electrostatic attraction. What about acetone? Well, it has an oxygen, but this is not directly bonded to a hydrogen. It only satisfies one of the requirements and so can only accept a hydrogen bond from water. It cannot hydrogen bond to itself. Meanwhile, down on the other end of the molecule, no hydrogen bonding can occur. We have to rely on weaker intermolecular forces, collectively known as van der Waals interactions. The two liquids can now remain mixed. We say that they are miscible, as long as they have enough in common from the perspective of their intermolecular forces. Speaking of the force, you could imagine our acetone and water as being like music fans and Star Wars fans at a concert to play music from film scores. They might not have everything in common when it comes to what attracts them, but enough to hang out together here. Now we need to add something else to the mix. Some dyes that can have enough interactions in common with the water and also with the acetone so that they can remain mixed with both. Food dyes are a good place to start, but a word of warning. You need the real deal. These are the sorts of food colouring that you tend to find in shops on the continent here. Avoid. The starch glucose base holds the colour as a suspension instead of as a solution. You may need to look online, but you want to find yourself the water-based concentrates a little bit like these. Which colours work best? Well, we're going to be using subtractive colour mixing here, so one way to think about this is the CMYK colour space, or at least in our case, cyan, magenta and yellow. The most dramatic mixtures will come from mixing pairs of those colours. Let's add the yellow. I'm using a dye that's high in tartrazine. Andrei Tretsiakov has got this to work in the UK with coumarin for the yellow food dye, but as I mentioned before, the coumarin that you get around here is not really any good. As we've seen, a good colour combination with yellow is blue, and we want a dye that's going to dissolve well in acetone, and the source for this one is going to be tiny bits of metallicized plastic known to you and me as glitter. Now, many people hate glitter. I get it. There are many reasons to hate it. When I was researching this article, I noticed on his obituary that the guy who is credited with having invented it also worked on the Manhattan Project, so you might say that there's two things that he did that we kind of wish that we could uninvent. But if you do use the glitter method, I can promise you, you only need a tiny amount. The dyes are really intense and last for a long time. Add that blue dye until you are satisfied with the shade of green that you have, and now is time for the trick. To get the dyes to separate, you want to add some good old-fashioned table salt. The solubility of salt in water is around 30% by mass at room temperature, which is why earlier on I suggested dividing the volumes into things that were easily divisible by 3. So in this case, with 15 ml, I'm going to add about 5 grams of salt. You don't need to be exact. That's more than enough to saturate the solution if it was just water, and of course a water-acetone mixture is going to saturate even more rapidly. Flip the tube upside down a number of times and give it a thorough shake, and then enjoy the effect as the green separates out to give our different colours. You may need to wait a few minutes, or it may happen instantaneously. Be patient, it will go. So what's going on? Well, let's return to our music from the films analogy. Everybody is happy until we change the offering. Put up a Star Wars convention, we might lose quite a number of our Star Wars fans as they perhaps feel more affinity for that. That doesn't mean, though, that some music fans have enough interest in the convention that they may also go. I mean, a film score or concert is a pretty broad event. Either way, though, we're definitely going to be polarizing our communities. As our colors separate out, we have some evidence of this. Although you may have started with a larger volume of acetone on top, you probably will end up with a significantly smaller amount afterwards. This indicates to us that the separation is not complete. What's going on in our solution? The addition of ions adds the possibility of new interactions. The water molecules point their slightly negatively charged oxygen atoms towards the positive sodium ions, and those essential hydrogen atoms needed to hydrogen bond to the lone pairs on the acetone, they're all pointing towards chloride ions, leaving little room for acetone to get in on the action. You can decant off the liquids and keep them for months at a time for shaking and demonstrating hydrophobic and hydrophilic effects. The dyes are quite stable, although I found that the blue dye does break down in UV over time, so maybe you'd like to store that one in the dark. All kinds of combinations are possible. But that yellow, blue and green combination I think is my favorite. And although it's a little bit more fiddly, you can get the effect without using glitter. Let's talk dyes. A common colorant used for PVC or PET-based glitter, and I emphasize this for those of you who may have come across some cellulose-based glitter, which doesn't work as well because you might find that the dyes dissolve a bit in water, is phthalocyanine. As a large neutral molecule, it will mix well with the sorts of non-polar substances in many plastics and won't mix with water. So technically we might call it a pigment rather than a dye. It's insoluble in water. These structures also have a colour overlay, which indicates to us how attractive they might be to the partially positively charged hydrogens of water. Tartrazine, with its 3- charge, is great at attracting water molecules and so follows them down to the lower aqueous layer when the mixture separates. Neutral dyes like phthalocyanine will stay on top with the acetone. Now, in the middle, we notice that we have this other dye here, a food dye, brilliant blue FCF. It's not quite as highly charged. This dye provides us with the possibility of avoiding glitter and the acetone altogether. Whatever food dyes you purchase, I do recommend trying them out to see how well they're going to partition in the final mixture. First, I tried the experiment just with the food dye, the acetone and the salt, separating it out just to see how well they would partition. The ones that I got from my food dye collection were mixtures of brilliant blue FCF, tartrazine, and the reds. The reds were particularly interesting to see how well they moved. My colorings used amaranth, erythrosine, and Ponzo 4R for their red dyes, and I would definitely avoid erythrosine for this demo. As you can see here in the left-hand pack of vials, it's too soluble in the upper layer. When Tom Kunzelman shared his problem with the acetone green mixture and asked people to try to replicate it, Grasny's Redder was able to get just regular green food dye to go because it incorporates brilliant blue FCF and tartrazine, and there was enough of a difference in solubility. No glitter required. To salt it out though, because there is more of a subtle difference in those polarities and their ability to mix, you're going to need more ionic strength than salt can provide. Grasny and Tom recommend potassium carbonate, but we didn't have any in stock here, and as you can see here, I found that sodium carbonate worked for me just fine. Tom says that he struggled to get it to work, so maybe you need to use the anhydrous form, which was the only one that we had in the cupboard. This is a rich source of ideas for inquiry, as well as a simple and powerful demonstration for intermolecular forces. Give it a try, and if you like it, give the video a like and a share. It always helps to spread the word. Otherwise, I'll see you in a couple of months. Bye!